Today we have a lecture by Professor Mikhail Klibanov at University of North Carolina in the USA. And he will speak about
convexification.
So please, convexification, yes.
All right, so now you see the
Professor Klibanov.
you see the title.
Yes, we can see it.
I will highlight by convexification 4 topics, and I will present entire convexification only for one problem, of course. I cannot do this for many. And then just maybe formulate theorems or just say, oh, it works for convexification, etc. So first topic is spatial and temporal monitoring of epidemics via coefficient inverse problem. Now, second topic, convexification for the retrospective forward problem of Minfield games. Next, third, CIP means coefficient inverse problem. Convexification for coefficient inverse problem of Minfield games. And finally, application of convexification to the 3D-dimensional problem of travel time tomography. In Russian, by the way, it's called inverse kinematic problem of seismic. So who are my co-authors? Academician Vladimir Gavrilovich Romanov, whom I know for 52 years already, by the way, we have good friendship. We argue with each other, sometimes very harshly, but we really like each other. So he is in Sobolev Institute of Russian Academy of Science in Novosibirsk. Actually, I'm myself from Novosibirsk. We had a great school of inverse problems led by academician Mikhail Mikhailovich Lavrentiev, who is the son of the founder of Akademgorod, Mikhail Alexeyevich Lavrentiev. So Romanov provided theory for travel time tomography. Very nice theorem he has proven. Second co-author is Yuri Averbuch. With Yuri, we had the first introduction of the tool of Kalman estimates in the Minfield games. Yuri is in Ekaterinburg, former Sverdlovsk, Krasovsky Institute of Mathematics and Mechanics. Now, my Chinese collaborator, Jinzi Li, I collaborate with him for 6 years very nicely in one of the leading universities in China, Shenzhen. And another collaborator is former postdoc of Jinzi, Zhipeng Yang. So Jinzi and Yang are responsible for computations in our team. I'm responsible for theory, meaning that I provide them a certain version of convexification for a problem, new problem, and then they do it. What about convexification? This is the first global converged numerical method for coefficient inverse problems which work without overdetermination. The problem is that 99% of numerical methods for nonlinear ill-posed problems, including coefficient inverse problem, they are based on least squares, okay? Least squares was introduced by one of the greatest minds in mathematics, Carl Friedrich Gauss in the 19th century. But being a super genius, Gauss well recognized that least squares works only for linear problems. Because as soon as you have non-linear problem, you cannot guarantee that your function is strictly convex, strongly convex. And therefore, you might have many local minima that you don't know what you're talking about, basically. Now, solution is unreliable. But since then, since Gauss, 200 years ago, right? Since Gauss, there was nothing else, okay? So people apply least squares everywhere in the world, okay? But the problem is that no mathematics is in anymore. There are thousands of books, tons of books, very heavy ones, but no mathematics. Why? Because all what you have is this, all right. Suppose I have solution, I know epsilon neighborhood of the solution, where epsilon is small. Then I start and I'm really great. But the question is, how do you know this epsilon? How do you know? And in practice, trust me, if you start to estimate epsilon in real numbers, then epsilon would be 10 minus 50 or something like this. In other words, those methods are unreliable, but they're still doing one, go without any mathematics. So this is what I basically said here. So convexification fixes this good drawback, but for a large class of nonlinear post problems and for coefficient inverse problems. I have introduced first this convexification in 1995, 1997 in two of my works. It was for a large class of problems, but at that time I was sort of scared to apply it numerically because there is one parameter, lambda. Lambda must be too large, and then it seemed to be that then nothing could work. But then I became less scared in 2017 and started to apply convexification with my co-authors to numerical studies, and all of a sudden numerical studies firmly confirm that we are lucky with convexification. In other words, lambda is, yes, maybe greater than 50 or whatever, but in practical computations, optimal parameter of lambda is between 1 and 5, which is fine. Why, by the way, why? It's like in any asymptotic theory. Considering, look, there are thousands of asymptotic theories in the world, especially in physics. What any theory says? Any theory says this. If certain parameter x is sufficiently large, then certain formula y is accurate, right? That's what I say. But then the question is, okay, I have specific model, specific problem, with specific range of parameters. What does it mean, large x and accurate y? What does it really mean? And the meaning of these notions can be described only by numerical studies, okay? And usually 3 is already a large number. X must be larger than 3 or something like this. That's the same as convexification. So the question is how the convexification works. There is a classical theory of Tikhonov, absolutely fundamental theory of Tikhonov, who was a founder of the theory of ill-posed inverse problems by his very famous paper in 1943. But his fundamental functional, regularization functional, he invented in 1963, 20 years later. And then it was a boom with regularization theory. But anyway, his functional is just least squares, basically, right? But it's very fundamental. I don't want to talk about this. If you ask me questions, then I will explain what the fundamental value of the Tikhonov functional is. But then I construct weighted Tikhonov-like functional, which nobody has done. I introduce a weight in this functional, and the weight is so-called Karleman weight function, which is involved in the Karleman estimate for corresponding originating differential operator. So as soon as I do it, then after some manipulations, I prove the theorem that if I have a bounded set B in Hilbert space H, B of D, where D is a diameter, but what is important, D is not small. If I assume that D is less than epsilon, then I'm again in this swamp with locally convergent methods. Basically, all locally convergent methods are nothing more than versions of the small perturbation approach. That's all what it is, okay? But in my case, d is not small. D is fixed, but not small. Any number. So then, if I have b of d, then I can choose such a parameter as I said, lambda, of the function h, j, that it is strongly convex on this b of d, and this is it. Still is done. This time thing here by Kalman functions. As soon as it's done, then I prove global convergence of the gradient descent method if starting from any arbitrary point of b of d, and rates of convergence are written explicitly. Global convergence of gradient descent method is sort of a miracle, I'm sorry to say. If you consider any classical book about numerical study methods where gradient-like methods are described, any theorem says again the same thing. If I start an epsilon neighborhood of the solution, then my gradient method converges. But if I don't start an epsilon neighborhood, then I have no answer. That's what basically any theorem says. But in this case, you do not need the epsilon neighborhood. That's a key here. So now, after this long introduction about general stuff about convexification, let me start from the first problem which I want to present. Coefficient inverse problem of the epidemiology. There is very well known, very great model of epidemics of Kermack and McKendrick, which was proposed actually 98 years ago, right? In Proceedings of Royal Society of London. And this problem this model is based on a system of 3 ordinary differential equations. All right? But as soon as you have ordinary differential equations, then what you have? You can describe your behavior of epidemics all in a whole. Basically, say how many say infected people you have in a certain city. But much more interesting question is how many people you have in certain regions of that city. In other words, it should be distributed. So even though this model is used basically by everyone, still American mathematicians Liu, Timbin, Lee, and Osher have extended the so-called SIR model. S means susceptible, I means infected, R is recovered populations. So they invented a system of parabolic partial differential equations. It was done in 1929, 4 years ago. In a very good journal, by the same journal, Applied Mathematics. So my idea is to solve inverse problem. So these are notations. Usually I work in very simple domains because inverse problems are very complicated by themselves. So if you solve it even in a rectangle, then you are glorified, okay? So these are the notations. And the system which was invented by these people is this. So rho S means the population of susceptible people. Rho I means infected population, and R means recovered population. Okay, as you can see easily, this system is nonlinear. But by the QS, QI, and QR are velocities. Velocities of these two-dimensional vectors in this case, or propagation of all these populations. Okay, so this parabolic system, of course, parabolic system, nonlinear parabolic system. You have Neumann boundary conditions 5 and initial conditions 6. But beta of x and gamma of x are 2 coefficients of interest. Because actually, whatever we say, but infection rate and recovery rates are unknown. So beta is the infection, and gamma is the recovery rate. Okay, and that's what inverse problem comes in. Now, just to clarify, since this system is nonlinear, it is nonlinear because you have products here. Then the classical theory, which you can find in the book, very classical book of Vladislav, Salonikov and Turaltsov, which was published in Russian in, I think, in 1965, and translated in English 1968, the best book in parabolic questions. So this book does not guarantee existence and uniqueness on a large time interval. It guarantees only on a small interval. I have no intention to improve the results of that book. I think they are not improvable. So we just assume that a solution exists, and solution is sufficiently small. That's all what it is. You see, it's very sufficiently smooth, C84. Why C84? But to be honest with you, in a field of inverse problems, people don't care about smoothness assumptions. Whatever smoothness works is fine, basically. Because again, inverse problems are so complicated by themselves that caring about smoothness is too much of a headache. What is coefficient inverse problem? So we assume that these functions satisfy that parabolic system as well as the smoothness condition, and we assume we assume that these functions are unknown. This should be unknown for certain domain Z, and unknown in omega, actually, unknown in omega, right? And known outside, okay? But as soon as we have this assumption, we must provide additional information to recover. So instead of initial conditions, actually, I don't know initial conditions. I know them only just to generate the data. I assume that my distributions of my populations are known in a certain intermediate moment of time. No, we can take t capital over 2, but any moment between 0 and c is okay. Why this is a reasonable assumption? Because look at the reality. At small times, authorities have no idea whether or not you have epidemics, okay? Who knows? So epidemics started to be noticed after a certain period of time. And that's what it is. In this case, all of a sudden, authorities became concerned, and they measured populations inside of the city at this time. Now, in addition to Neumann boundary conditions, I also know Dirichlet boundary conditions, but not on the entire boundary, only on a part of the boundary, gamma t. And of course, I know Neumann boundary conditions on the entire boundary, which are functions in 10. Okay. If I know boundary conditions, Neumann boundary conditions, so excuse me, Dirichlet boundary conditions, what does it mean? This means that at this boundary, I measure populations. Suppose you have flux of populations through certain part of the boundary, and you arrange certain stations there where you measure how many people will go through. Okay, so having all this information, I must find beta, gamma, and all these three functions. If I know beta and gamma, then of course I can solve this forward problem. But if I don't, then that's a problem. And my procedure allows me to find entire 5-dimensional vector simultaneously. So the first step of the convexification is I assume that beta 1 and beta 2 are positive, which is okay because number of susceptible and infected people is not 0, but positive. And then I go back to my system, substitute c equals t capital over 2, and express my coefficients through the solution. That's trivial algebraic manipulation. What is not trivial here? B1, B2 are known, not a big deal. I assume that my velocities are known, but dt is unknown. In other words, I don't know the derivative of my solution of my equation, the time derivative. All right. So then what I do, I differentiate the system with respect to t. In other words, introduce a new vector function v. As soon as I differentiate, then of course Newton-Leibniz formula gives me this calculation backwards. And then beta and gamma are expressed. But again, V1 and V2 are unknown now, period. So anyway, after that differentiation, after the substitution, all that, I obtain another parabolic system, but for function v, which I call V1. V1, and I have integral differential operators, actually. S is nonlinear function. And I know what? I know Neumann boundary conditions from the previous case on the entire boundary, and I know Dirichlet boundary conditions 19 on part of the boundary gamma. Still, I am not good here because I have dt under integral, and dt is here. It's not very convenient. So what I do, I differentiate the system 19 again. Yes, that's what I say. In order to introduce the function, vector function v2, which is derivative. And then instead of these three equations, I obtain six-dimensional vector function w, and then I obtain the system 21 of six nonlinear parabolic partial differential equations. As you can see, the problem is very much non-trivial, very much. It would be non-trivial, by the way, only even if it would be linear and I would know Dirichlet and Neumann boundary conditions, but do not know initial condition, okay? It's already non-trivial problem. This is 10 times more non-trivial because you have no linearity here. Again, parabolic system with no initial conditions. Now, we in our obtained what boundary value problem, or these functions on the boundary, they're called lateral Cauchy data, which is exactly the truth. So now convexification. The first step to do is to derive Kaliman estimate. Everything is based on Kaliman estimate. I forgot. I have introduced the method of Kaliman estimates in my work with Bugame in Доклады of Academy of Science in Russia in 1981. This is a single method, still single method in the entire field of inverse problems, which works for problems with single measurement data, okay? Now it's called Mikhail Klibanov method. But at that time, I was concerned only about uniqueness theorems for inverse problems. Now, actually, the convexification is a version of that method which works for numerical stuff, okay? For numerical stuff. That's very important. So that paper, I said I introduced Kaliman estimates in this problem. This was the first paper, which is now called seminal paper, to be honest with you. So Kaliman function phi lambda. Lambda is large parameter, 22. Now I introduce a space, a subspace of H21, which consists of those functions H21 which have a zero Neumann boundary condition, entire boundary, and zero Dirichlet condition on gamma. So the Kaliman estimate for this operator, Kaliman estimates, Kaliman actually, those estimates were invented by Kaliman in 1939. A few days ago, I sent to Tatiana that paper of Bugame and Klibanov, as well as the original work of Kaliman, by the way, in French. So Tatiana, if you want, you can share this with others, okay? It's public.
Yes, surely. Just now or after the main lecture?
It's up to you.
Maybe after. Better.
Okay. What I'm saying is that, as I said in my remark to Tatiana, that it was just genius paper of Kahneman, but only 9 pages. 9 pages. Very genius discovery. Right, in any case, so since then it was generalized in many ways. I mean, his work. I did it. My impact is that I do it for continuous problems, uniqueness and numerical methods. But people do it for other problems. So in any case, what was going on is for any Kahneman estimate, estimates only the principal part of the operator, only the principal part, not anything else. And what is this? In other words, it doesn't care about lower order derivatives. Okay. So C over lambda, 1 over lambda is large parameter, so small C over lambda is small, of course. It stands at the derivatives in the principal part of the operator, right? UC and UXX. But then all of a sudden, large parameter stands at the lower order derivatives. Okay? That's very important. So basically what it means, these are basically parasitic terms which can be taken care of using regularization. But what this means, by the way, if I would solve only problem for this operator, okay, for principal part, then this quadratic operator is not a big deal. The function would be strongly convex on the entire space. No, just after some manipulations and all that, but it would be strongly convex. But the problem is that in my, let me show you. You see, the system 21, it contains nonlinear terms. That's a problem. And nonlinear terms are with lower order derivatives. So I must somehow suppress them, dominate them, these lower order derivatives. And they are dominated because actually this Kahneman estimate says to you that they are dominated by the principal part of the operator. Of course, you must use phi lambda, Kahneman weight function. Now in a lemma, I worked, unfortunately I missed some formulas here. The lemma is this. Again, it was Mikhail who discovered this lemma first in 1991. But anyway, the lemma is this. You have Voltaire operator, okay? Look. You have Voltaire integral operator. Right? And that's the key for inverse problems. Before me, Voltaire operators were not involved in that investigations of Kahneman estimates. But Voltaire operators occur in inverse problems. That's very important. Okay? All of a sudden, and that's again my lemma of about 44 years ago, integral with Voltaire operator is estimated through the function itself. Which means what? Which means that basically I don't care about this operator, about this integral. Now I do what? I consider an arbitrary number R. Remember I said about arbitrary diameter of the set on which we solve problem by conjugation. Now R is sort of diameter if you finish, radius if you finish. So R is an arbitrary, and B of R is the set of all vector 6-dimensional functions, 6D, which are in this space, again, sufficiently smooth, which exactly have the same, which is important, boundary conditions, Dirichlet and Neumann. In other words, if you compare two guys, they must have the same boundary conditions. But norms of all vector functions in this B of R is less than R. In other words, as I have promised, I solve on a set of arbitrary diameter, but it must be fixed. No, if you consider Sobolev embedding, then B2R is actually in C26, and you have this inequality. And then I do what? Then I consider that convexification functional. C is a Tikhonov regularization parameter. If phi lambda would not be here, then this is exactly Tikhonov regularization functional, nothing more. But phi lambda makes a difference. And L, what L is? Oops. L is the operator of this integral differential equation, nonlinear. So I minimize this functional. This multiplier is just balancing factor because phi lambda is actually large. So, but C is between 0 and 1, so I should somehow balance. That's what it is. But that's constant anyway. And the central result about strong convexity of G is said. First of all, this function has Frechet derivative at each point. And the first statement is actually trivial. Not trivial, but simple. Next, there exists, suppose lambda 0 is that parameter of Kaliman estimate, theorem 1. Then we can find such a large parameter lambda 1, which depends only on these parameters, which is greater than lambda 0, and another number C1, which depends on these parameters. And if you consider regularization parameters like this is small, right? Remember I said there are parasitic terms in Kaliman estimates. Let me show them. Where are parasitic terms? Here are parasitic terms. You see there with minus sign. But fortunately, this minus, okay? So, and basically this lambda kills that parasitic term. So if we have this thing, then the functional is still strongly convex on B of R. In other words, the following strong convexity estimate is valid. Okay, the strong convexity estimate. That's very important. And another point. Here should be this term. By the way, there exists a unique minimizer, but on closest set. You see, you don't know whether minimizer exists or not, but actually it does on the closest set. If it would be inside, then derivative would be 0, right? But if it is on a boundary, then derivative is not 0. Nevertheless, this inequality holds. And this theorem implies the accuracy estimate. All right, you have minimizer, as I promised actually. You must minimize, you must estimate, in Tikhonov's theory it's called regularized solution, by the way, regularized solution. To be honest with you, if you consider 99% of works on regularization theory, you cannot see an estimate of accuracy of the regularized solution. People say something, but they don't estimate. I'm sorry. But here, the Kaliman estimate allows you to do that. So what we do, we assume that there exists exact solution. By the Tikhonov theory, you must assume existence of the exact solution in our solution without noise. Delta is the level of noise in your data. So you assume this. Now B star of R is the same thing as B of R, okay? But instead of R, I use R over 3. Again, this is global convergence because R is arbitrary, so R over 3 can be anyhow large. So we consider minimizer of the function on the entire set, B of R. And we assume that this minimizer belongs to B of R over 3. Why? This is reasonable to assume because of that estimate, because of the accuracy estimate. Okay. So then we construct the gradient descent method, as I promised. We take arbitrary point in B of R over 3, arbitrary W 0. Then we construct just a simple gradient descent method, which is 32. So all of a sudden, that theorem, the main theorem, implies this not 5.1, actually 2. That theorem 2 implies that this gradient method converges, globally converges to the exact solution as long as delta tends to 0. In other words, first of all, what is very important is that Wn, they all must be in the set B of n, B of R. If they jump out, then you have to use gradient projection method, which is not good. Gradient projection method is very inconvenient for numerical implementation. But the theorem said that they don't jump out of B of R, and convergence estimate holds. You see? Convergence estimate is not a big deal, not a bad story. Theta is less than 1, so everything is fine. Delta is your noise level, basically Gödel-like estimate. Everything is fine, everything converges. Now the full convergence theory is constructed, and it is convexification who allows you to do this. So conclusion is this: convexification provides a key factor which any method needs, the global convergence of the gradient descent method. If it doesn't converge globally, you obtain a solution, but then people can ask, is this solution reliable? Are you sure it is yes or not? And you don't know how to answer. Now the numerical studies, when we consider minimization of that functional, then the gradient behaves like this. You see initially it's not very good, but not that the case, and it is absolutely clear that we should choose a stopping criterion as soon as the gradient less than 0.01. When we started to work on this many years, in 2017, right, 8 years ago, we were not experienced that we were trying to get a 10 to the minus 11. It took hours and hours to compute because of this behavior, okay? But 10 to minus 2 is fine after about 150 iterations, 150 iterations. Now images, we do not want to cheat neither ourselves nor the readers. And what this means that we want to challenge ourselves. I like to challenge myself in science. And challenge ourselves means that we should image complicated structures. If you consider just letters, which everyone knows, they're very complicated for imaging. They are not convex, right? They have edges and they have voids. Nevertheless, with 3% of noise in the data, 1, 2, 3%, we image quite well these very sophisticated letters, A and omega. So this is just detailed description of convexification. I will go easy. Very fast, I meant. The Milfield games. I got involved in Milfield games when I was amazed by one work in December 2020. 2020 what? 2022, right? The Milfield games was invented by great French mathematicians, Lasser and Lyons, as well as great Canadian, I think they're engineers, Huang, Keynes, and Mohammed. What is very good, what is really amazing in this theory, that it can describe almost any societal phenomenon. So all of us know how many words people use in the newspapers and everywhere in the social media to describe some social events, blah, blah, blah. But all of a sudden, after certain nice effort of mathematical modeling, almost any, I'm not saying any, but I said almost any societal phenomenon can be described by the system of only two parabolic partial differential equations, nonlinear, which is a mean-field game system. But if you have such a great story, then you must pay the price. And the price is that first, these two equations have opposite directions of time. One is up, time is going up, in other words, time is going down. Next is nonlinearity of both equations. All right. Now, next is one of the equations contains an integral operator, which was never done in, at least I don't know about those works, in parabolic partial differential equations theory. But the main challenge is that it is unclear what is the principal part of the operator is. Why? Because Laplace operator of solution of the first equation is a part of the second. So you don't know what is going on actually. And this was the reasons why prior to my works in the last 2 years, there were no uniqueness theorems for forward problems, no stability theorems. In other words, when you put some data input data, you must know how stable you are with respect to noise in your data. Actually, if you solve forward problems, they will say this is why all these estimates, which we know in classical course. No rigorous numerical methods even for forward problems. No rigorous theoretical numerical investigations for inverse problems. But with Yuri Averbuch first, we introduced Kahneman estimates in this field. And these 4 points were addressed immediately. In addition, we introduced the ideology of Tikhonov, actually, ideology of ill-posed problems. So if omega is bounded domain, then mean-field game system is this. F is any nonlinear, almost any nonlinear operator. As you see, it's very inconvenient point here is that you have integral operator of the solution of the second equation. You see, V is the price or value function, whatever you call it. M is the density function of agents. But you see, consider the second equation. I said about the biggest trouble. You consider it carefully, then you will see that actually it contains Laplace operator of V, which is the kill here. What is the principal part of the system? Nobody knows. And only Kahneman estimates can handle this. So we have Neumann boundary condition. Conventional initial terminal conditions, I don't see them on my screen, but they are in 36. And they do not guarantee uniqueness, by the way. Do not guarantee uniqueness. Okay. This function f characterizes the interaction between players, especially this operator, integral operator. Whereas this term is local interaction term. This global interaction, in other words, if agent is far from you, then how this agent influences you. And this is described by that integral operator. But if it is closed, then it is described by this operator. So what is a retrospective problem? Retrospective problem is that in addition to those conditions 36, I introduce terminal condition for M. Next, I introduce another space of functions, and this is a Kalman weight function where lambda and nu are large parameters. So what is interesting is that exactly the same Kalman weight function must work for both operators, plus and minus. Otherwise, this is not good. This Kalman function does not work for your system. So the first Kalman estimate is this. Again, lambda and nu are large parameters. And the second Kaliman estimate is for minus. So first is for time running down, and this for time running up. Next, we have proven Lipschitz stability estimate for this system. So if f is a good function, basically, and we have some restrictions by arbitrary constants. And suppose that we have two triples, V1, V2, at the final moment of time, M1, M2 in final moment, and M0, M1 and M2 in initial moment of time. Then that Kaliman estimate allows you to prove Lipschitz stability estimate. In other words, the problem is Lipschitz stable, which is very good. Very good. Which means uniqueness, by the way. As soon as you have, if these guys are equal to each other, then you have zero here, right? Now, the next question is, okay, all my methods now are start from theory, proof uniqueness, and then global conversions. That's my style for recent years. How to solve this problem? Again, convexification. We consider those two operators of in the left-hand side of Milfield game system with Neumann boundary conditions. We have the same terminal and initial conditions, as I said. Again, analog of the set B of R. Again, Kaliman function. Consider three functionals. First one is L1, second one is L2, and third one is Tikhonov regularization functional. Gamma is regularization parameter. So then we minimize that function on the set B, minimize this function G, which is sum of three. Minimize that function. So, and the full analog of the previous strong convexity theorem works here. So this image, again, we choose the letter C and see how does it change. It's not bad, actually. Again, we use only letters because they're complicated. We address some other forward problems. In this case, only V is known at T equals T capital, but initial conditions here. Stability estimate. Now, if both functions are known either in final moment of time or initial, then we still have further stability. Sometimes you have known lateral Cauchy data, and the kernel has special form. I don't know formulate. Now, coefficient inverse problem. If we know kernel, but not entirely, we don't know this multiplier. Then how to solve it? All right. First, we get a new. I remember I said about Kaliman estimate for Voltaire operator. Now it's modified, much better. In the first estimate was 1 over lambda, where lambda is large parameter. But here is 1 over lambda to 3/2, which is better. So basically, that's a theorem about stability and uniqueness of that inverse problem. And now, of course, convexification again. So we find this function k of x, multiplier at the kernel. Again, the analogs of that theorem works. And the image is very good. Actually, this is the first image in the entire business of Milfield games. They do it, but not rigorously, and not so much images. And finally, the problem of travel time tomography in 3D, this so-called Fourier canal equation, okay? This is the single most challenging inverse problem I am aware of. The first result was obtained in 1905, 120 years ago, by Herr Glotz. Herr Glotz solved this problem in a one-dimensional case, specifically for geophysics. He assumed that Earth is a ball, and the speed of propagation of seismic waves depends only on the radius. He presented actually explicit solution, and you know what? Geophysicist uses all the time that solution for the last 120 years. In other words, everything what we know about this Earth, say that it has mantle, what the certain layers and all that, everything is known from geophysical data and applying that solution of Herglotz. Fundamental result, actually. But the question is, many people worked on the question, what about if speed of seismic waves depends on the region? And there were no global conversion numerical methods before our problems. So we solved for the first time that problem of Herglotz after 120 years in three-dimensional case. So we consider Riemannian matrix, n of x is the refractive index. Then tau, what tau is? You have a source of waves, x0, and tau of x is the observation point. Then tau is travel time. How much time does your signal need to propagate from x0 to u, okay? And this integral over the geodesic line, which is generated by this Riemannian matrix. So then there is a well-known A-canal equation. Again, many people worked on this, but only uniqueness theorems and only in the overdetermined case. So the travel time tomography problem, or inverse kinematic problem in seismic, is in Russian, is that if we know function x is 0, that's a problem we consider. Suppose that x0 runs along the vertical axis of the cylinder. And we know the refractive index in a small sub-cylinder which is surrounding this vertical axis, okay? But then we also measure tau on the surface, on the lateral surface of that cylinder. We must find C. Here is a picture. So source runs along this line. We know everything in this small cylinder, and we measure on the surface, on the lateral surface of this big cylinder. And we must find coefficient. So again, convexification works. This first application of convexification. We again image three-dimensional cases. Again, letters. So this function B, letter B, and this is its image. This is cross section, maybe not well seen, but this cross sections, exact, reconstructed. This letter O, by the way. And this is a image. Again, cross section. Cross section is fine. It's fine. So, what is the summary? Oh, by the way, recently, by speaking about field games, we just got the results very recently. We got the results in two directions. First direction is forecasting of public opinions using mean field games. We did it now for simulated data. The paper is almost ready. And we will do this for experimental data. Again, using mean field games, experimental data, using my methodology. All right, forecasting. In other words, you give some initial conditions for public opinion, and you don't know what public opinion will be in 3 days from now. That's what we do. Second, I forgot what to say second. Anyway, classification is a very versatile method, which is applicable to a broad class of coefficient inverse problems with non-overdetermined data. So this is the only method which has the global convergence property. Thank you very much. I finished.
Thank you very much for the very interesting talk. And now it's time for questions.
Yes.
Jack, Alex,
Meanwhile,
before-
ask you
maybe before questions, I will translate
Yes,
a
please.
Kleiner College award. Here you can see it. In this year, Professor Klibanov received the award for excellence research. You can see it.
I was the only one who received it. I was the only one.
And I will also show how this award is looking. Please give me 1 minute. Here it is. Yes, so that's what I want to show you.
Thank you, Tatiana.
Good.
I was the only one. I had many competitors, but I was the only one. I have about 12 publications every year in Q1, Q2 journals. Almost all about convexification or some variations of this.
I wanted to ask you if this approach is applicable to inverse spectral problems.
Inverse spectral problems, right? All right, I will show you something. That's a good question.
Yeah.
First of all right, let me show something. It's not easy to deal with. Now all this technical stuff. Do you see this?
Yes.
This book was
Yes.
published by the Grutter 4 years ago, okay? And in chapter 10. Let me go to chapter 10. Wait. Plenty of things about convexification here. Here. Yes, we did it for inverse spectrum problem for experimental data, by the way, from microwaves. For the Helmholtz equation. Where is Helmholtz equation? In 3D case. Here. 10.5, okay? Again, these are experimental data. This is not a joke anymore. I had a grant from the US Army Research Office. Let me show the convexifications here, all the theory. Let me show our experimental device design and results. You see, there's a theory where again I construct convexification, prove some theorems. Here is experimental device which we built, by the way. So this is a source of microwaves, okay? This detector, by the way, small one. And the detector moves along this wall. It covers the square, 1 meter by 1 meter, step size is 2 centimeters. Here is a box in which you put sand. Since it was the US Army which supported this, then we were trying to discover mines, landmines. Landmines were things which mimic landmines are here inside. But we pay attention to the background. If you consider some other works, for example, there is a French group in the Institute of Fresnel, then they very much isolate their device because you don't know what kind of waves would come back to you from reflection. We don't do this. We just do this in a regular room, you see, a regular room. All right, so this is the image of the metallic cylinder. By the way, these are our data. Before getting real data, you should, in a non-trivial way, you should process them, and that's what you. Actually, the classifications apply to this data. And this image. This is another image. This is a bottle. Bottle of water. What is interesting? This bottle of water models just a real mine which was used by Germans during the Second World War. Models is just a real mine. Glass mine is also called. Nevertheless, we image it and we give both shape, we see one cup, and refractive index as well. Refractive index of water we need. So this is again the letter. Unfortunately, we don't have entire P, but we have something. This letter A, we still see something without this plan, this part. What else? This letter O. So yes, classification is applicable, but you most likely are interested in a one-dimensional case of inner spectral problem. I will show you this result as well. By the way, about this book, I sent a bunch of messages to Tatiana when we exchanged. And in my signature, you'll find the website of this book, so you can buy it. As well as for another book, which is about Milfield games. It will be published in a few days. But anyway, let's see. Now one-dimensional case. This is more complicated. I mean, more complicated to find. Let's see.
But probably at this point, a reference would be enough.
No. I like everything to put in.
Okay.
Here. Do you see the share? You see the share?
Yes,
No?
yes.
Share? So this is a paper of 2020, right? Smirnov was my graduate student. So this is exactly the inverse scattering problem. One-dimensional, okay? You must find C. But certain transformation, which is well known, actually reduces this to the classical Gelfand-Levitan problem in 13. But Gelfand-Levitan equation is not good here. Why? Because it needs spectral data, all that, plus, I'm sorry to say, my friends, but there is no uniqueness theorem for Gelfand-Levitan equation. I'm sorry to say. But here we have, of course, uniqueness and global convergence and fine R. Again, convexification, some reconstructions. Oh, reconstructions. Reconstructions. All right, that's what I did I answer your question?
Yes.
Did I address your question? All right.
Okay, may I ask you?
Yes. Yes,
a
please.
question?
Go ahead.
Misha, nice to hear you, and thank you very much for nice talk. And I have a naive question. You claim several times that your problems are non-over-determined. For instance, unlike the boundary control method is in one dimension. It exactly well determined, but it was already in 2 dimensions. It became over-determined because we find a function of 2 variables from data, which is a function of 3 variables. Can you, on this physical level, demonstrate of your example that you exactly try to determine a function of, say, 3 variables from another function of 3 variables?
I cannot demonstrate on physical level, but it is absolutely clear from the statements of the problems which I gave. All right?
Yeah. Just.
Well, I can explain this. So, for example, consider that first problem which I did epidemiology, right? What you do, you measure on the boundary, say, Dirichlet boundary condition in Neumann. So each of these conditions depends, in a 2-dimensional case, depends on 2 variables, right? One variable is, let's say this is a circle, okay? One variable is your angle, and another variable is time. 2 variables,
yes.
period. And your coefficient also depends on 2 variables, x and y. This is it. And in the travel time tomography is the same thing. You have source, right? The 3-dimensional case. You have source, which is 1 dimension, which is running along the straight line. And you have measurements on the side of the cylinder. The side of the cylinder is 2-dimensional. So all my methods work only for non-overdetermined data.
Okay. Thank you. It was my question.
Again, the single method which works for non-overdetermined data is Karaman method of mine, okay? Either it is numerical or it is numerical. There are some other versions of, say, Karaman weight function method, etc. But basically, the method of Karaman estimates works only for non-overdetermined data. Again, by the way, there is another version of the convexification, so-called Karaman contraction principle, but it's also based on Karaman estimates. It was invented later.
Okay, thank you, Misha. It is clear.
Thank you. More questions?
I should say who invented the second. Second was invented by my colleague Longuin. All right. Any other?
Okay. If there are more
It's
questions.
Karaman weight function. Karaman contraction principle was invented by my colleague Longuin and his co-author. All right.
Okay.
His co-author is Tuilia. Right.
If there are questions, comments. So we had a very good discussion. Thank you very much for the very interesting talk. Thank you.
Thank you very much for this opportunity. I enjoyed it. Bye-bye.
Thank you.